And also for me, a welcome to all of you. I hope you all can hear me well. Do you hear me in the back? Is this loud enough? Great. Yeah, I'm happy that so many of you are here and are interested in my topic. This project has occupied me for a better part of the last year. It started out as a suggestion that this could be my master's thesis. And then it grew and grew, and we went to this conference and there and got more and more input. And now we're here and have quite achieved something. All right, I'll start with a quick project history, how this whole thing started. ONE LOGIC had a similar kicker like this about 1.5 years ago at PASTAS 2017. They also had cameras and they wanted to detect goals and do a couple of stuff, but it was really a night and dagger procedure. So they did it like, they said two days prior to the conference, said, okay, let's make a kicker with cameras and super fancy. I think you can all imagine how that worked out. So we said we restart the whole project in April 2018, and we start with basic features first. So we only want to take goals and have some match metrics and predictions. Who will win this match? This is really easy. We just have to add light barriers inside of the kicker which detect when the ball goes through. And the rest is basically software and communication. And that's also the interesting part. Second step would be that we add cameras to the whole thing. This is now the second step, as you see it here. And with the cameras, we can create a heat map where the ball is most frequently. We can add metrics about ball possession and about the speed of goals, the shot speed. Yeah, when I started developing this, I started really small. This was the first time I managed to simply get a light barrier to work with a Raspberry Pi. And then 2 weeks later, we had our first demo users. Yeah, and actually, a couple of weeks later, we took this whole thing, put it into the transporter, and drove all the way to Hannover to a conference at Continental. Here we have the kicker and our proud managing director, Rossi. And like this looks great. It was totally in the entrance hall of the whole thing. But behind the scenes, it looked like this. Yeah, you see now there are still some cables, but we've got the whole thing much more managed now. All right, I'd like to proceed now to the architecture of the whole thing, how it works. It's basically three big steps, three big parts in the whole thing. For one thing, the kicker itself, where we generate the events and detect the events. Then on a kicker server, we process the events, and then later in ONE Data, the analysis platform we use at ONE LOGIC, there we generate insights and make predictions about the current match. Yeah, as you probably have already read by now, the kicker runs on a Raspberry Pi and Python scripts and has the light barriers, as I already talked. Kicker server is a simple Node.js server. Yeah, about the Raspberry Pi, most of you might have heard of it before, and just the reasons why we decided to go for it is that it's really cheap, pay about $30 or euros per piece. It is a full-powered operating system, which makes it much easier to automate things. So I have like cron tabs that start at the startup of the whole thing, start the server and the detection and everything. I don't have to do anything manually. And also we have the full power of the internet available to us. So there's no need to write our own TCP/IP stack or anything. Then there are many libraries and tutorials for basically everything. For example, for accessing the hardware of the light barriers, and it has Python compared to a regular microcontroller, which usually runs only a very old set of C. You're quite limited with what you can do in a quick time. Yeah, there's some drawbacks. Most importantly, the quality of the SD card is really important. The first couple of tries I had, whenever I did something wrong and it crashed, I had to get a new SD card because the SD card was corrupted and it wouldn't start anymore. Then, after a couple of weeks, I've said, okay, I'll just buy something that is €2 more expensive, and now it doesn't matter if it crashes, it just works. Yeah, then also the setup time. To configure everything, you need, or I need about 3 to 4 hours, because there are a lot of moving parts that need to play together. I managed to bring that down to 2 hours with using a pre-made image, but I'm just not there yet that it's really reasonable to produce it in a mass scale. And the third thing, it has only digital pins, no analog pins. It doesn't matter for the current setup we have, but I at some point tried to include a distance sensor, and for that you either need a ADC converter or you need analog pins, and it would be more comfortable in many cases to have analog pins. All right, then to the actual event detection. I'm not sure how well versed you all are in basic electronics, so I'll give a quick introduction. This is an electronic signal that we would like to have, meaning when nothing is happening, we have the green line. When something happens, a goal, for example, or when you press on the button, it peaks, goes back to normal. Unfortunately, that's not how electronics work, because it looks more like this. Meaning that it goes around the threshold all the time, and it will all the time it will switch between on and off without actually anything happening. Additionally, when something happens, then it doesn't just go up and stays there. It goes up, down, up, down, up, down, until it stabilizes at some point. So what we need is a so-called pull-down resistor. Anybody heard of that before? Okay, good. I'm not talking bullshit here, and I'm not talking it, although you already know it. So a pull-down resistor basically makes the electronics pull down to 0 in normal operation, and if then some external interference comes, they will still go up to 1. Meaning, after we add that, it looks like this, but we still have that problem with the bouncing at the start, and that's why we need debouncing of the button. And this is just a quick motivation for the code I want to show you, because this is as simple as it gets to read out or to get an event in Python from a hardware pin. Yeah, so we import this library, the GPIO. GPIO is short for General Purpose Input and Output, meaning we can send and receive anything on these pins. Yeah, we disable warnings. We set the mode to board. There are two modes, either the board where we access the pins on the numbering, so 1, 2, 3, 4, 5. And there's also another numbering system, the BCM, which is more aligned to how the pins are on the processor. Yeah, and then we say, okay, we want it on pin 8. And we set up this pin as an input. Oh, sorry. Here we are. But as an input, and as I explained previously, we need the pull-down resistor. You can either do the pull-down resistor physically, or like here, you can also put it in software. Yeah, and then we add some event listeners, and okay.
Yes, we are done.
Oh, okay, thank you. And we say at a bounce time of 20 milliseconds, meaning it will only call this function once in 20 milliseconds and will not do it repeatedly. Yes. All right, so much to the event generation and event detection. Obviously, a lot more happens, but this is the core of what we do there. Then in the Kicker server, there's actually nothing special going on. We receive the events from the kicker via REST API. So it's really simple. There's with each event, there's an event ID, event type. So that's either match started when some people press on the button, or goal scored, or match finished. That's it. And then there's a timestamp, and when there was a goal, then basically who scored the goal, if it was team white or team black. The kicker server takes this data and aggregates the data. So it saves it to a database. It generates matches from single events, and also it triggers OneData via a microservice. OneData, maybe you have heard of it before, looks approximately like this. We define our workflows graphically and connect the different parts with these lines. And then we connect these results, we have these down there, the dark blue ones, to a report, which would look like this. And this is the version of the report when you don't have cameras. So there's two versions of the whole setup, with cameras, without cameras. Without cameras, we show some more of additional data, like the time, the distribution of results, and distribution of match times. Now, it gets more interesting when we look at the architecture with the camera setup. What we add is basically here the camera, which runs on a separate machine, simply because of the data it generates. We cannot possibly send all the data from a camera to OneData and process it there, because we're already at the limit what the USB cable can do. Now imagine sending that over the cloud in real time. No chance. So we have a separate hardware, separate computer that runs the software to detect everything on the kicker and the camera. It runs with C# and OpenCV. OpenCV is a open source library for processing images. Some of you might have heard of it before. And it's optimized for speed and also for correctness, obviously. C#, simply for that reason, that's one of the languages that's widely used at the company, is supported by OpenCV, and is supported by the framework of the camera we use. For the ball tracking, it's also a very interesting part, how we do the ball tracking. It's basically 5 parts, or 5 steps. First, we grab the image from the camera. Then we convert it to HSV. I will later show what HSV looks like. Then we filter the image. We apply some morphological operations. And then we find the contours of the remaining of the ball we want to track. And get the point. But to give you some motivation, this is what the dashboard looks like with camera. Meaning we have a heat map here, we see where the ball went along. This is actually quite a typical heat map for one of the first goals, because the ball is injected here, then goes back and forth sometime, and then there's a shot to make the goal. About the image grabbing, first step of the whole process. This is the image we get from a camera. See, it's not too bright, it's not too sharp, but it's enough. The thing is, if we would have a better camera with higher resolution, that would just mean that our processing gets slower because we have more data to process. And this is perfectly enough. Here you see the red ball, and as long as we see that, we're fine. First step, as I already mentioned, is converting it to HSV. HSV stands for, H is for hue, S for saturation, and V for value. That's a different color scheme. And in the HSV color scheme, your first portion of the color is actually the color on a rainbow scale. As you see here, basically on a 360-degree plane, 0 is red, then it goes over yellow to green, blue, into purple at some point. And this is great because we can simply say we want we want to remove or filter out everything that's not between a value of 10 and 20, for example. That way we keep only one color. Then saturation is the intensity of a color or the purity of a color. And then value is the brightness. We use this also a little bit to filter, but we use most importantly the hue value to filter the ball. Yeah, this is what a HSV image looks like of the previous image we had before. And here you see now that all the stuff that is actually white is in a different color, and the ball is white. And you can filter it out more easily here. Yes, then we apply static filtering, meaning for each image and for each pixel, we check if it is within specific boundaries. And if it is not, then we set it black. If it is, we set it white. And we receive this. You see, I can also, as a human, I can already pretty good detect that here's the ball. We have some white sprinklers here and here, but they don't matter. But for a computer, we want to go one step further and apply some filters on it. We dilute it and erode it so that the ball actually gets one single connected piece, and all the other white sprinkles are gone. Okay, once again, to see it all next to each other, we go from the original raw image we have here, we convert it to HSV, we filter it, and then we apply the morphological operations to make it more clear and more suitable to our needs. And remember, the last step was to find the contours. The contours is really hard to explain. I'm using a built-in function from OpenCV there. It basically gives me the contours of the object I find there, of all objects I find. And when I simply take the largest of these objects, of this area I find, and take the center of these, and this is the ball. And it works surprisingly well because we don't have any other white sprinkles in there. Now, obviously, the question is, how fast can we do this? Or rather, how fast do we have to be? What do you think? How fast can this camera go? How many frames per second? Some wild guesses. 200? It depends a lot on the settings of the camera, actually. But yes, we are getting to 200 frames per second. But first, let's take a look at how fast we actually would need to be and why we need to be that fast. As I said previously, we want to be able to detect shots and measure the speed of shots. Now, I know that the ball moves up to 10 meters per second, sometimes even faster. And let's say we want a ball location every 5 centimeters to track the ball. That's simply because we have the typical shot distance is about 20 centimeters, and I would want at least 4 data points to reliably measure the speed there. Meaning that we need an image every 5 milliseconds, which translates to 200 frames per second, which we need. Now, there are 2 bottlenecks to the whole thing. One is acquisition speed, meaning how fast the camera can make pictures, but that's not the real issue. Because you can increase that as much as you want simply by decreasing the time the sensor is open, the time it takes to take a picture. It's currently at 2000 nanoseconds, but we could go lower. The only difference it would make is that the image would be a little bit darker. The much bigger bottleneck, what's going on here? The much bigger bottleneck is the data transfer. The transfer from the camera to the computer, and we're limited by the USB cable basically we have there. Now, USB cable can do about 300 megabytes per second. And now let's do some calculations and some theory. Full resolution of the camera is 1280 times 1024 in grayscale, meaning 1 byte per pixel. that means 1.3 megabytes per frame. If we have full resolution in color, then we're up at 3 bytes for red, blue, and green, because for each pixel we need three channels, 3 bytes. Then we're at 3.8 megabytes per second. And now you maybe see the problem. In grayscale, we can get up to 230 frames per second transferred, but in color, only 78. And I really worked on this for a couple of weeks until I realized what was happening, because I was doing everything to increase the speed, and I wasn't sure if it was the camera or my computer being too weak to process it in the time or anything, until I realized, okay, it's a transfer, and it doesn't work with colored images like this. So what I did, I reconfigured the camera so that it sends me the raw data, not RGB data, but raw data as it is taken in the camera, and that's in a Bayer matrix. A Bayer matrix is how most modern cameras, electronic cameras, work, because there are no, in image acquisition, you cannot actually see, or you cannot measure colored light. You can only measure brightness. What the hell? Okay. Yeah, you cannot measure colored light. You can only measure brightness. But what you can do, you can say, okay, for this pixel, I want to measure blue light. For the next pixel, I want to measure green light. For the next pixel, blue light again. And that's exactly this matrix we have here. And later on in software, you can calculate the average color for each of the pixels from the neighboring pixels. The thing that this gives us is that we again only need 1 byte per pixel, because we have on this byte we have the blue intensity, and then on the next we have the green intensity, and then the blue again, and in the next slide it alternates between green and red. This actually tries to resemble the human perception, because the human eye sees much more green and blue light than it sees red values. Yeah, we can do that, and later then we can convert the whole thing back to a normal RGB image, and then do our operations I showed previously. So they convert it to HSV, apply the filter, the morphological operations, and so on. All right. Yeah, this is the project as I've developed it the last couple of weeks and months in a quick summary. Do you have any questions so far? Please feel free to shoot now. Or would you rather like to try it right now? Yes?
I have a question about data transfer. There's like compression, and then decompression, it takes more time.
The thing is that what you can do at the camera is quite limited. You can configure it some way, but you cannot set a compression there. Also, I'm not sure how well it would play with real-time then. There was a question first, yeah?
Yeah, more like a practical background question. Did like your employer pay for you to do that? And if
yes.
So, why?
Because it's a great company. Yeah, I'm getting paid to say that, obviously. The reason we want to do this is we want to have a showcase for One Data, which is a product we develop and we sell, and we want to show how we can connect real-time Internet of Things with our platform, and how we can generate insights. Because the kicker is something everybody can connect to. They know how it works, they know the basics of it, so it's really easy to explain something about it.
Why
Yes?
do you have to convert the raw data to RGB first? Can't you convert it directly to HSV?
Yes, in theory we could, but OpenCV doesn't offer this conversion. And obviously I could convert it myself, but that would probably be 100 times slower than the conversion of OpenCV. Yes?
Why that high resolution?
Sorry?
Why this high resolution?
We actually have a lower resolution a bit because we only need a portion of the image, because the camera takes, let's say, takes everything until here and until here, which we don't need. So we crop it so that we only have this. But I tried to go a little bit lower to have it, let's say, only half as high the resolution, and it gets harder to detect it, because the lower the resolution is, the bigger is the impact of some random artifacts. Because as you saw in if we go back, in this image, there are some black sprinkles in there, and there are some white sprinkles in here. And right now they don't matter, because it's just 1 pixel in a million. But the lower the resolution is, the more they will matter. And at some point, we will have we will jump around, because the image of the ball will be just as big as the artifacts around. Yeah, Sarah.
Can you explain your equipment you have here?
My equipment?
Yeah, the equipment, the server and everything.
Oh yeah, sure. Well, it's basically what I explained, or what I showed already. We have a kicker. Underneath, there is some hardware installed. Feel free to have a look later. It's basically a lot of cables and a Raspberry Pi. The 2 light barriers. And back here, the powerful desktop machine to do the image processing. And in our current setup, the server we have is also on the Raspberry Pi, because that's just quick for a setup like this, where we move the kicker around. What we are currently developing is that we have one central server that serves for all, simply for easier maintenance. Yeah, basically that's it. There's not that much more equipment. There's the camera, obviously, and there's this aluminum frame, but that's not really an interesting part of the equipment, because that's not electronic. Yes?
Why is there no additional lamps near the camera?
There should be some, but they broke about a couple of weeks ago. And like we had them and relied heavily on the lamps, and when they broke, actually at Pastas this year, so the first real time we wanted to show it to people, and it worked the day before. When we moved it there, and didn't work. It was like, oh fuck, what are we going to do? But we discovered it actually works without. If the ambient light is bright enough, ideally daylight. And at Pastas, it was really great, because we were in the Audimax building at the university, and there's a glass roof, and it was a bright day, so we had a lot of brightness, and we're really lucky. But now we discovered, yeah, it works even in darker settings. Like this looks very bright, but it's actually really dark compared to outside daylight. It still works if you configure it correctly. The only drawback is that you have to reconfigure it every time you move it somewhere else.
What kind of configuration?
You basically have to configure the thresholds for the filter. So for this, from this step to this step, you need to define the thresholds for the brightness value, the saturation value, and the color value, because the color is also different based on what type of light you have. If you have cold light or warm light, or yeah. Also, one of the problems we have with normal light like here is that the light is flickering, actually. We don't see it because our eyes or our brains is too slow, but the camera sees it. Because the camera goes with 200 images per second, but the lights around here, they go with 60 frames per second, meaning that it's usually alternating between one darkish and one bright image all the time, and that's a problem also, but it still works, and we're happy about it working. Obviously, if we want to work it in any setting, we would have to add some spotlights to make it more even lighting. Yes?
What are some more insights that you can gather from image data? You see on the dashboard, there's like the score and a heat map. What else can you put on the data?
Well, basically everything you can think of. We're mostly limited by what we can fit onto a screen, onto a report. You could I'm actually going to show it, what we have. Yeah, this is the report with the camera. What we show here also is the history of speed of shots. We could also, with more analytics, we could show the distance of a speed, or the distance of a shot, sorry, or the possession rates, like how much percent of the time is the ball in white team's possession or black team's possession. You could, anything you can think of in a professional soccer game, where they display ball possession, number of passes. You could do all of this if your software is smart enough. With the normal data you get from just the scored goals, you can, with the dashboard here, you can not only predict the outcome of a match, but you can also predict the duration, or the remaining duration of a match. You could try to predict who makes the next goal, and maybe at what time. So you could say, okay, the next goal will happen in 15 seconds by white team. Obviously, the fancier your predictions get, the less reliable they are probably going to be, especially in a really random setup like a kicker, where a lot depends on the individual skills and also really just random, because there are some very good players who can control everything, but most people just shoot and it goes somewhere. Yeah, Sarah?
Do you know if it's planned that we do like further advanced setting of the kicker with personalized dashboards where I can see my rank and I can see who's my best match or my best partner for winning?
Yes, that's one of our goals for the next couple of months, is that we add RFID readers to the whole thing, and everybody at our company has an access token which looks like this. Damn it. It looks like this. This is a normal RFID token which we open the front door of the office with. But we can also use it to authenticate at the kicker and to have personalized ranking, for example. So who is the best kicker player in the company, who makes the most goals, who plays best with partner, and so on. And then you could also increase or improve the performance of the predictions, because the predictions probably depend a lot on the individual players and less on general assumptions you can make. Yeah.
You currently focus on the position of the ball only. Did you think about extending the analysis onto to watching which of the players, or what's it called? I don't know.
Figures, Figuren, yeah.
Which of the figures are used to do shots if you turn unnecessarily and stuff?
One of the ideas I had when we started the whole thing is to add acceleration sensors to these bars. Mostly because I thought the image tracking wouldn't be feasible, and I thought the acceleration data would be easier. But yeah, you could, from the position of the ball, you could already determine which of the players is used to shoot. Because when you see, okay, the ball is just moving around comparably slowly, and then suddenly it gains a lot of speed, then you know when it started to gain the speed, that's where the shot started. Yep.
Yeah, I just thought some of the positions are ambiguous because you can move quite far.
Yeah.
So not exactly which.
I know what you mean. Yeah, it's not. Yeah, you can only determine from where the shot was made, but not which individual player. Maybe you could still do that because you have an image of it, so you could also analyze the position of the bars if they are like this or this. And also with these here, we even have numbers on the back of their jerseys, so we could try to read that with computer vision and see who shot. Okay, that was, yeah.
Why only OpenCV, why not ROS? Because ROS processes the images faster and object detection becomes easier.
Which framework?
The robotic operating using the quadcopters for the object detection.
Okay, I haven't heard of that before. Mostly we wanted, is it open source as well, or?
Yes.
Okay.
It's runs on Linux.
Okay. Yeah, it's basically I picked something that did the job and was available and worked with the existing ecosystem we had. But I have no money in that. It's just was the first I took. So. Okay. Any more questions? Any more? If not, I'm sure you will have some more questions later on. But now I would proceed to actually inviting you to play and try it yourself. And we will have a small competition to do so. So if you want to participate, please go to either Pedro or Sara or me and sign up basically with a partner, obviously. There's only teams who can play here. And we have 2 of the ONE LOGIC mueslis we would give to winner. And there's one, or actually, quick question here. How many of you want to participate? How many want to try it and play? Okay, it's getting more and more. Okay, yeah, it's probably going to be hard to have a normal tournament here because yeah, there are just so many teams and there's only so much time. So I would say we change it up a little bit, and both of them go to the 2 people who have the highest speed shot. So it doesn't matter who wins; it's just about getting a high speed shot. Okay, sounds like fun? Okay, great. Then thank you very much for your attention, and